Hello guys, welcome to our class for today. For today we are going to be looking at magnetic fields, and the content of this class will cover magnetic fields. We'll also look at the magnetic field around the straight conductor carrying current, and then the direction of magnetic field lines on a current carrying conductor. So in that we'll look at the right hand grip rule and the Maxwell Corkscrew rule. Then we'll look at how the magnetic field around a solenoid and how magnets are made, and then demagnetization. So the course for today, or the class for today, will cover almost everything that we need to know about magnets. Okay, almost everything that we need to know about magnets. So guys, I hope you have your writing materials ready. As I've always said, please always get yourself prepared for each of our class by getting your materials ready and then staying in a quiet place where you will not be disturbed. So this is Normal Science Resource Online. It's your your online video class, and you are welcome to this class for today. But please, before we go to our class, subscribe to our channel if you have not done that. Click on the notification bell so that when we upload a new video, YouTube will notify you. Also give us a like, give us a thumbs up, give us positive comments to encourage us. That's okay. We are doing a lot, right? We've done a lot. You can see it from our playlist on our video channel. So, and we are taking it gradually and step by step. And so far, we've been able to cover almost all the topics for SS1 and SS2 curriculum, and we are in the SS3 classes. So give us a positive comment to encourage us. So thank you so much, and let us go straight to our class for today. Okay, so as I said, today we are looking at in this particular class we are looking at magnetic field. So what is a magnetic field? A magnetic field is just a region around the magnet which the influence of the magnet can be felt or detected. So if you have a magnet around you there, you can feel the effect of the magnet if you bring a magnetic substance close to the magnet. So the region around that magnet where you can feel the effect of that magnet is what is called the magnetic field of the magnet. Okay, all right. So it is also the area around the magnet in which it can attract or repel objects, or in which a magnetic force can be detected, is called the magnetic field of that magnet. Magnetic field is a force field, and as such is a vector quantity. It has both magnitude and direction, so you need to take note of that, because you can be asked which of the following is a vector quantity. So magnetic field is a vector quantity because it has both direction and magnitude. The presence of a magnetic field can be demonstrated by using a compass needle. When the compass needle is placed in such a field, it will swing and settle in a definite direction, showing the presence of a force. Alright, so if you don't have a compass needle, you can actually use iron filings. You can use iron filings to detect the presence of a magnetic field. Is that okay? So we also have what is called magnetic lines of force. So magnetic lines of force, okay, if you look at the picture under, you will see some lines. You see some lines with arrows. These are actually called magnetic lines of force. These lines of force, they are not seen. You cannot see them with your eyes. So they are also called imaginary lines. So magnetic lines of force are imaginary lines along which a free north pole would tend to move if placed in the field. The magnetic lines of force do not really exist, hence they are called imaginary lines. So the patterns of magnetic field, these are the patterns of magnetic field. These are the various patterns of magnetic field. So magnetic field patterns can easily be observed using iron filings. The magnet is placed on a paper and iron filings are sprinkled lightly on the paper around the magnet. The paper is now tapped gently. The iron filings will be seen to turn and settle in a definite direction. So if you have such an experiment, we see that when you have a north to south pull, right? If you have a north to south pull, you see that the lines of force are moving from the north to the south pole. So in this case, you have an attraction. Alright, so if you have a north and north pull, okay, so you see a repulsion, and then in the center you have a neutral point. Okay, then if it is just a bar magnet, the lines of force will run from the north to the south, and that is why you have these arrows. So please take note, these are typically objective questions that you can see, so that you should know the direction or line of force. Direction or line of force from the north to the south pole of a magnet. So if you have like poles, you have repulsion. If you have unlike pole, you have attraction, right? And the arrow must move from the north to the south in all instances. Please take note of that. So this is what magnetic lines of force is all about, and then the patterns of magnetic field. All right. So now we'll look at magnetic field around a straight conductor carrying current. So assuming you have a straight conductor, a straight wire that is carrying current, what is the magnetic field or magnetic field lines around that conductor? In what direction do they move? That is what we want to study now. Okay, so for you to carry out this process, one, pass a straight conductor through a cardboard, sprinkle iron filings on the cardboard, connect the system to a battery and switch on. Then open the switch and place a compass needle and switch on current. Observe the direction of the compass needle. The direction of the compass needle will give you the direction of the lines of force. The compass needle shows that the magnetic field lines of force are observed to be arranged in concentric circles around the wire as shown above. So you will see that the magnetic field, they are arranged in concentric circles like this. The direction of the field lines depends on the direction of the current. If the direction of the current changes, the field line also changes in direction. Now, for you to know the direction of the current or the direction of the field lines, there are two rules. We have the Maxwell Corkscrew rule and the right hand clenched fist rule. Okay, we have the clenched fist rule and then the Maxwell Corkscrew rule to tell us the direction of the field lines. Okay, so the Maxwell Corkscrew rule. The direction of magnetic field lines around a straight current carrying wire can be identified using the Maxwell Corkscrew or clenched fist rule or right hand grip rule. The Maxwell Corkscrew rule, what it says that if a right-handed corkscrew is turned so that its tip travels along the direction of the current, okay, if you know what's a corkscrew, that screw that they use to open wines is a corkscrew. So if you point it downward, as if you want to open a wine, and that side that you point the tip, if that tip is the side of the current, if that tip shows the direction of the current, then the direction of rotation of the corkscrew gives you the direction of the magnetic field or magnetic lines of force. So you can just do that now as you are listening to this video. Just put your fingertip on your paper. Point your fingertip on your paper, right? Point your fingertip on your paper. If your fingertip is pointing towards the direction of the current flow, then look at the direction of your other fingers. All right, you will see that the other fingers, they are moving in a clockwise direction. That shows the direction of the feed lines. You can do that now as you are listening to this video. Just do it. Point your thumb as if your thumb represents the corkscrew, and that also represents the direction of the current. Then look at your other fingers. The other fingers, the direction of the other fingers give the direction of the magnetic field or lines of force. And if you look at the video, the diagram on the video, you will see it there. So this is what I just explained. If this is the direction of your corkscrew, you see that the magnetic field lines, they are in a clockwise direction. Now if you reverse the current, now reverse your hand, turn your hand upward. Yeah, I just said that point your thumb upward before. Now point your thumb upward and let the upward thumb represent direction of the current. Now look at the direction of your other fingers. You can see that your other fingers are showing the direction of the magnetic field, just as it is in the diagram that you are seeing in front of you. Okay, so when current is going in, the direction of magnetic lines of force is clockwise. When current is going out, the direction of magnetic lines of force is anti-clockwise. I'm sure this is clear, and this is very, very important and key. This is important and key. I hope you understand this. Then another rule that can help us too is the right hand grip rule. The right hand grip rule says that if the straight wire is grasped with the right hand so that the thumb points to the direction of the current, then the direction of the finger indicates direction of the magnetic field. So this is also the same thing with what we have just discussed. So if this is your thumb pointing in direction of the current, then the direction of these other fingers gives you the direction of the magnetic field, and that is what you have here. Okay, so when you reverse it, the magnetic field line was so reversed. All right, so I hope this one is clear and you have been able to understand that. Okay, magnetic field around the solenoids. So this is a picture of a solenoid. A solenoid has is made of copper wire, insulated copper wire that has many turns that is worn around a cylindrical core. The cylindrical core can be a form of a soft iron on the center here. So when current flows through the solenoid, the magnetic field lines around the solenoid, they are similar to that of a bar magnet with a north and south pole, and that is exactly what you have here. Okay, so current, the magnetic lines of force, just like in a bar magnet, they flow from the north to the south. So this is the south and this is the north pole. So this is just the picture of a solenoid, and this is the magnetic lines of force around the around a solenoid. Okay, the way they are with a bar magnet, that is also how it is with a solenoid. Right, so there's no more story in this place. All right, guys, so thank you so much. This is where we're stopping this class for today. We hope you have enjoyed the class, and if you have any question or any concern, please let us know, and then we are here to assist you and to help you. So thanks. Before I leave, please give us a like, subscribe to our channel, click on notification bell so that when we upload a new video, YouTube will notify you. This is Normal Science Tutors Online. Hope to see you in our next class. Have a nice day.